All right, let's talk about the fundamental theorem of calculus. There are two parts to this, parts 1 and part 2. Now, as you may imagine, this is pretty important. Like you might say it's fundamental to the theory of calculus. It is really important. The fundamental theorem of calculus is the connection between derivatives and integrals. It's what ties all of calculus together. So like I said, there are two parts. This is part 1. And here you can pause and read this yellow box here. So we've got some continuous function here. So you've got some function here, and it actually doesn't have to be continuous, but let's say it is. So you got some continuous function. Now, this is a function of t. This is f versus t. And what I'm going to do is I'm going to call this point A, and my variable is going to be x. So I'm going to pick some t value out here at x. And I'm going to define this new function. Capital F of x is the area under this curve from A to x. So in this case, it would be that positive area minus that negative area. And I'm going to let x vary here. So x can go along the t-axis here. So that defines a new function. As x changes, I get different amounts of area. So capital F here is the amount of area between A and x. And x is going to vary along the t-axis. That function will not only be continuous, it'll be a nice, pretty function of x, it'll also be differentiable. It's guaranteed to have a derivative. And moreover, here's the fundamental part, the derivative of this capital F is lowercase f evaluated at x. So this is the connection between derivatives and antiderivatives and integrals. The derivative of an integral, those in a sense cancel each other out and just give you what's inside. But this is important here. Our limits on our integral here will be from a up to x. Notice I'm using a different variable inside here. We call that the variable of integration, or it's just a dummy variable. T here plays no role. When we're taking the derivative of this guy, what we do is we take the integrand and just replace the t with an x. So like for a quick, silly example here, they called this guy little g. I'm going to call him capital G. So capital G of x is the definite integral from 1 to x of 1 over t cubed plus 1 dt. So that's a well-defined function. If you wanted to, you could plot out this graph here, y equals this function. And this guy will spit out the area between 0 and x for any x value. And it's actually defined for, let's see, x equals -1, we would have an issue. So we need to stay away from there. Otherwise, this guy is fine. Now, who cares about that? That's not the point we're getting to. If I take this guy's derivative, all I do to take his derivative is take the integrand, and instead of writing t's, I write x's. There it is. We're done. The derivative of an integral is, they in a sense just cancel each other out. Now we got to be careful. This has to be a number, and it can be any number. And this just has to be x. What if there's some function up there? What if I have f of x is the integral from, say, a up to u of x. So up here I have a function of x, little f of t dt. Then we have to use the chain rule. And that's really what this is. It really is chain rule. We could prove it, but we're not going to right here. Then capital F prime will be little f here evaluated at x times the derivative of whatever this guy was, u prime of x. So we replace the integrand, we replace the variable with x. Oh, sorry, this should be f evaluated at u of x. Times u prime of x. Okay, so if this guy up here is not just x, but is just a function of x, then we have to use chain rule. Okay, we'll do some examples like right here. So we've got some function of x there. So I could say u of x is square root of x, which we usually think of as x to the 1/2 power. Then capital F prime of x. We're going to take our integrand here, sine of t. We're going to replace the t with whatever was up there, square root of x, and then multiply by the derivative of what was up there, which will be 1/2 x to the negative 1/2. Okay, what if our top and bottom limits are both functions of x? See, in these examples, the bottom was just a number, and I really don't care what the number was. I remember when I learned this, that always bothered me. Well, what if that's a 10 instead of a 1? It won't matter because the derivative of a constant is 0. That's why that number doesn't matter. But if there's a function there, if we have x's in top and bottom, then we got to do a little more work. So f of x here, I'm just recopying the problem, is the antiderivative or the integral from x to 2x of t cubed dt. I want to write this. I'm going to go through the work of writing this the same way we wrote all the other ones, by splitting this integral up. I'm going to write this as the integral from x to 0 plus the integral from 0 to 2x of t cubed dt. Why 0? I literally just picked a number. I could have used any number at all. I could have picked 7. Now, what if 0 is not between x and 2x? It doesn't matter. Remember, we already learned that the integral from a to b of f of x dx is the integral from a to c plus the integral from c to b, f of x dx. We're allowed to split up integrals, and typically when we do that, the number c here will be someplace in between a and b. So what this says, if c is in between them, is under my curve here, this area plus this area equals the total area. That's how we usually use this property. But this statement is true no matter where c lives, even if c is over here somewhere. So the statement I've written here is true no matter what. So I'm allowed to split this integral up by going from x to 0 and then again from 0 to 2x. Now, why would I want to do that? Because the fundamental theorem of calculus wants me to go from a number up to a function of x. Okay, now this one goes backwards. Look at that. I wanted my x on top. I've got the 0 on top. I'm allowed to switch my limits and write that first one as negative 0 to x, t cubed dt. And I'm going to leave this second guy alone because he already looks the way I want him to. Now they both look the way I want them to look. They both look like this. They're both the integral from a number up to a function of x, and then some integrand involving t. Okay, so what's this guy going to be? When I do the derivative the derivative of this, that negative is going to come along for the ride. And that t is going to get replaced by x. Here, that t is going to get replaced by 2x times the derivative of what's up top. And you might say, well, why didn't you do that here? Why didn't you do? I did. The derivative with respect to x of x is just 1. So there is capital F prime.